Bismillahirrahmanirrahim. So let us look at this problem. A Y-connected balanced three-phase generator with an impedance of 0.4 plus J 0.3 ohms per phase is connected to a Y-connected balanced load with an impedance of 24 plus J 19 ohms per phase. The line joining the generator and the load has an impedance of 0.6 plus J 0.7 ohms per phase. Assuming a positive sequence for the source voltages and that VAN is equal to 120 angle 30 degrees volts, find the complex power at the source and at the load. So we note that this is a Y-connected three-phase source, and it is balanced, right? So, and the load is also Y-connected and it is also balanced. So this is a balanced Y-Y system, right? So let's first draw the diagram, which would be helpful in solving the problem. So this is a three-phase generator, right? So, and it has source impedance of 0.4 plus J 0.3 ohms per phase. So this is the source impedance here, right? So this is, for example, VAN, and then we have the second phase, for example, VBN, right? And this also has this same impedance, 0.4 plus J 0.3 ohms. And then we have this third phase here with the same amount of impedance, right? And this is the line joining the source to the load, and this also has an impedance which is 0.6 plus J 0.7 ohms per phase, right? And this is our load here, which is Y connected again, like the generator. So yes, this has an impedance here, right? Like this one, and this is the again the line for the third phase, and this also has an impedance here. So this is, for example, VAN, this is VBN, and this is VCN, right? And this is the source impedance, 0.4 plus J 0.3 ohms. This is also same, 0.4 plus J 0.3 ohm. The same here, 0.4 plus J 0.3 ohms. And the impedance of the line is given out to be 0.6 plus J 0.7 ohm. Here again, 0.6 plus J 0.7 ohm, 0.6 plus J 0.7 ohm. And the impedance per phase is 24 plus J 19 ohm, 24 plus J 19 ohm, 24 plus J 19 ohms, right? So the phase voltage for one phase is given. So VAN is given out to be 120 angle 30 degrees volts. So now it is a balanced system, right? So in a balanced system, the power delivered by each phase is the same as the other phase, right? So the power in the three phases is equal. Power delivered by the source in the three phases is equal, and the power absorbed by each phase is equal, right? So what we can do is we can simply find out the phase current of a single phase, right? And then from that current and the phase voltage we can find out the power per phase, and then when we can multiply it by 3 to find out the power for the three-phase system. For example, here this is VAN for this phase, and we can find out the current in through this phase here, right? And note that this is a Y connected system, so the line current is the same as the phase current. For example, if this is the line current IL, this is the phase current IP, then IL is equal to IP for this system here. IL is equal to IP here for a Y connected system. And this is for example phase A, so we denote this current, may denote this current here as IA, this current here as IB, so this current here as IC, right? So we can find this current IA, which is this line current and also the phase current, and then we can find out the power delivered by this phase, for example P for example the power delivered by this source of the VAN source, denoted by A as minus VAN multiplied by the conjugate complex of IA, right? So this will give us the power of a single phase, power being delivered by a single phase. As this is a balanced system, so the power by the three phases, all the three phases, will simply a multiplication of this power multiplied by 3. So this will be 3, for example, multiplied by PSA, or 3 multiplied by PSB, or the 3 multiplied by PSC, right? So we can find out the power from a single phase and then multiply it by 3 to find out the total power being delivered by the source. For our verification, let us find out the power through each phase, and let's see whether this formula holds or not. So for example, let's find PSA first. So we already know VAN, and we can find VBN, and it's given that this is a positive sequence, right? So if it's a positive sequence, then VBN is equal to VAN angle minus 120 degrees, right? And VCN will be VAN, and that will be minus 240 degrees, minus 120, then further minus 120. Minus 240 is the same as plus 120. So this is also VAN, VCN is also equal to VAN plus 120 degrees. So here the angle for VAN is 30 degrees. So VBAN from here is in effect 120 and angle 30 multiplied by 1 angle minus 120 degrees, right? So VBN is equal to 120 angle minus 90 degree volts. So this is VBN, right? And a similar manner, VCN is given by VAN angle plus 120, or we can use minus 240, right? So VAN angle 120 degrees. So VCN is equal to 120 angle 30 degrees, 1 angle 120 degrees. So VCN is equal to 120 angle 150 degrees volts. So we have found out the phase voltages for all the three phases, right? So this is the balanced system. So in a balanced system, the line current IA for the first phase is given by VAN divided by the impedance for that phase. Now the impedance for this phase is the total impedance of this source impedance plus this line impedance plus this load impedance, right? So this Z is given by the sum of all the three impedance. Z is equal to 0.4 plus J 0.3 plus 0.6 plus J 0.7 plus 24 plus J 19. 19. So Z is equal to 0.4 plus 0.6, that is 1.0, plus 24, that is 25, plus J 0.3 plus J 0.7, that is 1, plus J 90, that is J 20 ohm. So Z is equal to 24 plus 25 plus J 20. So let's convert this into polar form also. 25 plus J, sorry, 25 and J 20. So that will be 32.02 plus J 38.66 ohms. So IA is given by VAN divided by Z. So VAN was found out to be VN is given out to be 120 angle 30 degrees. So 120 angle 30 degree divided by sorry, I wrote this in again in rectangular form. This was to be in polar form. 32.02 angle 38.66 degrees ohm. So this is 32.02 angle 38.66 degrees. So the current IA is given by 120 divided by 32.02. So that is 3.75, and 30 minus 38.66 is obviously minus 8.66 degrees here, 66 degrees ampere. So this is the line current for phase A. Similarly, the line current for phase B is given by VBN divided by ZY, but we can find it from here also because this is a balanced system. So IB is basically IA angle minus 120 degrees. So IB, the magnitude remains the same, 3.75. So minus 8.66 minus 120. So that is minus 128.66 degrees amperes. And IC, the line current for the phase C, the magnitude remains the same, and that is minus 8.66 plus 120 degrees. So minus 8.66 plus 120, so that is 111.34 111.34 degrees amperes. So this is the current for the phase C. So now we have the phase voltages for the three phases, and we have the phase currents for the three phases, right? So we can find out the power in each phase using this kind of a relationship, and we will see that the power in each phase is the same. So let us find out the power in phase A, for example. So power in phase A, PSA, is equal to minus VAN conjugate complex of IA. Minus here signifies that the power is being delivered by the source. So and we are using the passive sign convention here, right? So PSA is equal to, this is minus, and that was to be 120 angle 30 degrees, and IA is 3.75 minus 8.66, but here we have to use the conjugate complex, so this sign of this angle will reverse. So 3.75 angle 8.66 degrees. So power in the source phase A is equal to 120 divided by 3.75. That comes out to be, this minus sign here, 450, and this is 30 plus 8.66, so that is 38.66 degrees volt amperes. So this is complex power, right? And we are uh, rather we should denote it using S, right? This is complex power, so it will be better if we denote this using S, right? Denote it using S, right? Here also let's denote this using S. This is complex power, right? So in rectangular form, so this will be 450 angle 38.66. This gives us 351.39. So this minus sign, let's keep this here, minus 351.39, and this is minus J 281.11 volt amperes. So this is the power being delivered by phase A of the source, right? So let's also find out the power being delivered by the phase B. So let's call this phase B, right? Power in the phase B. So that will be minus VBN multiplied by the conjugate complex of IB. So SB is minus VBN. So VBN was found out to be 120 angle minus 90 degrees, right? So 120 angle minus 90 degrees, and multiplied by IB, conjugate complex of IB. So IB is 3.75 minus 128.66, and we are to use the conjugate complex. So that will be 3.75 multiplied by 3.75 at an angle of 128.66. That was minus 128. Now we are using plus 128 here, right? So the power in the phase B is equal to again 120 multiplied by 3.75. The magnitude remains the same and the negative sign here remains the same, minus 450 and minus 90 plus 128.66. This is again 38.66. This is the same result as here. So the rectangular components will be the same, minus 351.39 minus J 281.11 volt amperes, right? Likewise, for the third phase, SC, this is minus VCN multiplied by the conjugate complex of this current IC. So SC is equal to VCN was found out to be 120 angle 150 degrees multiplied by, and IC was found out to be 3.75, and here we are to use to conjugate complex, so that will be minus 111.34 degrees, right? So SC, so 120, 3.75, this minus sign here, this again is minus 450, right? And 150 minus 111.34 will again result in the same value as 38.66 degrees volt amperes, and the rectangular components again will be the same, minus 351.39 minus J 281.11 volt amperes. So as you see, This is a balance system, and in the balance systems, the power for the three phases remains the same. So what we could have done is we can now add the power in the three phases to find out the total power being delivered by the source, or we can simply multiply the complex power being delivered by the source S is 3 times uh, this minus VP IP conjugate complex, right? And this we have found out to be minus 450 angle 38.38.66. So this is 3 multiplied by minus 450 angle 38.66 degrees. So the power being delivered by the source is 450 multiplied by 3, so that is 1350 minus 1350 angle 38.66 degrees volt amperes, and this can be expressed in rectangular form also. 1350, and the angle is 38.66. So this is 1350 angle 38.66. So this is 10 minus 1050 and 847.38 minus J 847.38 volt amperes. Let me just reconfirm this. 1350 and the angle was 38.66. so that is, sorry, 10 this is 105. Let me just again check this in the rectangular form. 1350 and this angle is 38.66, so that is 1054 and 843.34 volt amperes, right? So this is the power being delivered by the source, right? So the power delivered by each phase is the same, and this is the total power being delivered by the source by the three phases. So this is the real power, 1054 watts, and this is the reactive power, 843.34 volt amperes reactive. This is P part and this is the Q part, right? And this is the apparent power, 1350 volt amperes. So if we are now interested to find out the power being absorbed by the load, then again power absorbed by each phase of the load is given by, for example, the phase A, the power being absorbed by the load phase A is equal to the IA square, right, multiplied by the impedance of phase A, right? The phase impedance, right? The phase impedance of A. So this will give us the power being absorbed by phase A. And as this is a balance system and the impedance of the three phases is the same, as we have found out the currents of the three phases are the same, the magnitude is the same, right? So equal power will be absorbed by the three phases. So the total power will be simply the sum of the three powers. So the total power absorbed by the load will be equal to the 3 times of this value. I mean the phase current squared multiplied by the phase impedance. So in this case the phase current IP is 3.75 in each case. So this is 3.75 squared, right? And um, the impedance was found out to be 25 plus J20 ohm, and we can express this in polar form also. So 25 and 20, and this is 32.02. Yes, we express this in polar form here, 32.02 and uh, angle 38.66. So this is 32.02 angle 38.66 degrees, right? So this is given by 3 multiplied by 32.02 multiplied by 3.75 squared. So that is 1350, right? So sorry, but we are not to use the total impedance here. We are to use, this is the total impedance. We are to use the impedance of the load, right? And the load impedance is given by 24 plus J19. So this is 24 plus J19 here, right? And 3 multiplied by 3.75 squared, and otherwise, because the power comes out to be the same, however, the power is being lost in this line here and in this source impedance here. So the power absorbed here is only by this impedance. This will be 24 plus J19. So that was a mistake. So 24 plus J19. So let's convert that 24 plus J9 into polar form. So 24 J19. So that is 30.61, and the angle comes out to be 38.37 degrees. So the power being absorbed by the load is now given by 3 multiplied by 30.61 multiplied by 3.75 squared, and that is equal to 1291, right? 1291, and the angle is 38.37 degrees volt amperes, right? And this can be converted into rectangular form. So 1291 at an angle of 38.37, this comes out to be 1012 1012.17 plus J 801 plus J 801.37 volt amperes. So this is the power being absorbed by the load, right? And this is the real power, right? The real power being absorbed by the load, and this is the reactive power, 1012.17 watts and 801.37 volt amperes reactive, right? And this is the 1291 volt amperes apparent power, and this is the angle of the impedance, load impedance 38.37 degrees, and cos of 38.37 degrees is the power factor of this load, right? So we now have determined the power being delivered by the source, which is this power, and we have now also determined by the power being absorbed by the load. We actually did not need to carry out or find out these phase voltages and all the phase currents. What we all needed was to find out a single current of the single phase, for example IA, and we already knew VAN, so we can then find out uh, uh, the power in a single phase, for example this power, and then we can multiply it with 3 to find out the total power, and then we can perform this step to find out the power being absorbed by the load. So it need not carry out these steps. These were only for demonstration to show that the power absorbed in each phase is the same in a balanced system, and the total power being delivered by the source in a balanced system is simply 3 times the power being delivered by a single phase.